Welcome to the recording on quadratic inequalities and two variables for Unit 9, Chapter 9 of Mathematics 2200. We'll be explaining when a solid or a dashed boundary should be used in the solution to an inequality and explaining how to use test points to find the solution to a quadratic inequality and sketching the graph of a quadratic inequality, of course, in the context of two variables. In recording 1A in section 9.1, we looked at what a linear inequality in two variables looked like. Here we look at a quadratic inequality in two variables. It has both an x and a y, and it looks like a quadratic function except that it uses one of these four symbols. It may be rearranged from one of these forms. So for example, this one here, if I brought the negative 3x squared and the 2x across the inequality sign, I'd have this form. Recall that in section 9.2 we looked at quadratic inequalities in one variable, and those only contained x's, no y's, and we graphed their solutions on number lines. Because we have two variables involved here, we'll need both our x and our y-axis involved, which means it's a two-dimensional graph. Shading will be involved. Now recall, if two variables are involved in an inequality, then we have to find all points x, y that can be substituted into that inequality to make it true. So for example, 0, 9. Let's see what happens when we substitute those values in. If I put the 0 in place of the x and the 9 in place of the y, I wind up with 9 greater than or equal to 1 times negative 1. That's a true statement. And it also makes the other inequality true. When I substitute 2, 5 in, here I get 5 greater than or equal to 5 times 1. It's true because I've got that equal sign there. 5 is greater than or equal to 5. But when there's no equal sign, it becomes a false statement. And I've completed the rest of the table. 0, 0 makes the first inequality true and the second inequality true. 3, 14 makes the first inequality true. 14 is greater than or equal to 7 times 2. It's actually equal to 7 times 2. But it's going to be false over here because there's no equal sign. Likewise here, negative 7 greater than or equal to negative 3 times negative 3 is what we end up with. But negative 7 will not be greater than or equal to 9. And it won't be greater than 9 either. Now, like we did with linear inequalities in two variables, shaded regions are meant to indicate the set of all points that will satisfy a particular inequality. If there's an equal sign in the inequality, it's a solid boundary, and if there's no equal sign, it's a dashed boundary. On the previous slide, we already did the calculations to see if these points satisfy this inequality. You can look them up, but 0, 9 is in the shading. That makes this first inequality true if you check the calculation. And here, it was also true. 2, 5 is on the boundary. It made it true in the first case, but only because of the equal sign. And in the second case, it was false because the equal sign wasn't there. And in the last case, negative 2, negative 7, that's outside the shading in both, and it returned false statements in both cases. We apply the ideas here. We have y greater than or equal to negative 2 outside of x minus 3 squared plus 1. That gives us the boundary y equals negative 2 outside of x minus 3 squared plus 1 with vertex 3, 1. So I set up a little table of values to help me graph it. 3 starting with the vertex. I plot my points from the table and use the symmetry of the parabola to get the other side. Keep in mind, this is an equals case, so it's a solid boundary. Solid, boundary drawn in. Now we need a test point, something not on the boundary. Again, it's most convenient to choose an x value and a y value that are the same, like 1, 1, 2, 2. It's hard to mix them up when substituting them in. 0, 0 is always nice too. That's the one I'll choose, and I'll plug it into my inequality to see if it satisfies. So when I do that, I've got negative 2 times 0 minus 3 squared plus 1, negative 3. 0 minus 3 is negative 3 squared. I get positive 9. times -2 is -18 plus 1 is -17. That's a true statement. Therefore, 0, 0 is in the shaded region. So I can simply use my highlighter here. Again, you can use your pencil, turn down its side. That's always nice if you use a standard pencil that you can sharpen. They're the easiest ones to do your shading with. And there's our shaded region. In this final example, we just have a greater than and the function is in standard form. But that doesn't perturb us because we're good at what we do. We can use -b over 2a to get the vertex at 2 and -9. So now x, it can be 3 or 4 for other convenient values. So calculating those points, I get points at 3, -8, and 4, -5. Then I use the symmetry of the parabola to get the other side. Our parabola will need to be dashed because there's no equal sign in our inequality. And now I'll just do the best job that I can to dash that parabola in. Now that I've completed my parabola, I choose a test point. My favorite is 0, 0, as you've probably come to discover. 0 greater than or equal, or greater than rather. 0 squared minus 4 times 0 minus 5. That gives us 0 greater than -5. That's true, so it will be in the shaded region. And therefore, our shaded region lies above our parabola. In review, a point satisfies an inequality if it makes it true. Use a dash boundary if there's no equal sign in your inequality. Solid if there is an equal sign. And here are the steps. Graph the boundary, determine if it should be solid or dashed, use a test point, and shade the appropriate region.